this matrix looks complicated. 85 entries, 5 rows, 17 columns, but the entire thing is nothing more than 4 simple pieces added together. Each piece is built from a single column vector and a single row vector. These pieces are called rank 1 matrices, and they are the atoms of linear algebra. Every matrix, no matter how large, is a sum of these atoms. Let's start with the simplest case. Consider the 2 by 3 matrix A with first row, 1, 4, 5, and second row, 2, 8, 10. Now look carefully at the rows. Row 2 equals 2 times row 1. Every entry in the second row is exactly twice the entry directly above it. 1 times 2 gives 2, 4 times 2 gives 8, and 5 times 2 gives 10. Because of this relationship, the entire matrix is determined by just one row and a set of multipliers. We can write A as the column vector U equals 1, 2 times the row vector V transpose equals 1, 4, 5. This is called an outer product, a column vector times a row vector, which produces a full matrix. This is in contrast to the dot product, which produces just a single scalar value. Let's verify this entry by entry. U is the column vector 1, 2. V transpose is the row vector 1, 4, 5. We'll build the resulting matrix one entry at a time. Entry 1, 1. U sub 1 times V sub 1 equals 1 times 1, which is 1. Entry 1, 2. U sub 1 times V sub 2 equals 1 times 4, which is 4. Entry 1, 3. U sub 1 times V sub 3 equals 1 times 5, which is 5. That completes the first row. Now for the second row, entry 2, 1. U sub 2 times V sub 1 equals 2 times 1, which is 2. Entry 2, 2. U sub 2 times V sub 2 equals 2 times 4, which is 8. Entry 2, 3. U sub 2 times V sub 3 equals 2 times 5, which is 10. And there's our result. The matrix with rows 1, 4, 5, and 2, 8, 10. Exactly our original matrix A. Every single entry is the product U sub I times V sub j. This factorization reveals the geometry. The column space of A, the span of its columns, is spanned by the single vector 1, 2. Look at the columns of A. They are 1, 2, and 4, 8, and 5, 10. Each one is just a scalar multiple of 1, 2. 4, 8 equals 4 times 1, 2. 5, 10 equals 5 times 1, 2. So all 3 columns lie on a single line through the origin in R2. That means the column space is one-dimensional. Now look at the row space. The rows of A are 1, 4, 5, and 2, 8, 10. Each is a multiple of 1, 4, 5, since 2, 8, 10 is just 2 times 1, 4, 5. So the row space is also spanned by a single vector, and it too is one-dimensional, a line through the origin in R3. Rank 1 means both the column space and the row space are one-dimensional. The vector U is a basis for the column space. The vector V is a basis for the row space. The outer product hands you both spaces directly. Now let's generalize. The rank of a matrix is defined as the number of linearly independent columns. If the rank equals 1, then the matrix is a single outer product. 1 column vector times 1 row vector. If the rank equals 2, the matrix decomposes into exactly 2 rank 1 pieces, and more generally, if the rank equals R, the matrix decomposes into exactly R rank 1 pieces. Now return to our 5 by 17 matrix from the opening. It has rank 4. So A equals U 1 times V1 transpose plus U 2 times V2 transpose plus U 3 times V3 transpose plus U 4 times V4 transpose. That's 4 rank 1 layers stacked together, not approximately 4, exactly 4, no fewer. Each layer captures one independent direction of information in the matrix. Rank 1 matrices are the atoms of matrix structure, but they have rules about how they combine. Let's see what happens when we add 2 of them. Take M1, the 2 by 2 matrix with entries 1, 0, 0, 0. It has one non-zero row, so its rank is 1. Now take M2, the 2 by 2 matrix with entries 0, 0, 0, 1. Again, one non-zero row, so rank 1. Now let's add them together. M1 plus M2 equals the matrix 1, 0, 0, 0, plus the matrix 0, 0, 0, 1, which gives us the matrix 1, 0, 0, 1. That's the 2 by 2 identity matrix. And the rank of the identity matrix is 2, not 1. So two rank 1 matrices sum together to produce a rank 2 matrix. This means the set of rank 1 matrices is not closed under addition. Remember, a subspace must be closed under both addition and scalar multiplication. Rank 1 matrices fail the addition requirement, therefore they do not form a subspace. The precise rule governing this behavior is known as the rank inequality. It states that the rank of A plus B is less than or equal to the rank of A plus the rank of B. Here is the intuition behind this result. The column space of A plus B lives inside the sum of the column space of A and the column space of B. This is because every column of A plus B is the sum of a column of A and a column of B. The dimension of that combined space cannot exceed the sum of the individual ranks. We already saw an example of this. Rank 1 plus rank 1 gave rank 2, hitting the upper bound exactly. But the inequality can also be strict, sometimes dramatically so. Take any matrix A with rank R and let B equal negative A. Both A and negative A have rank R, so the bound allows the rank of their sum to be as high as 2R. But A plus negative A equals the 0 matrix, which has rank 0. So the inequality permits dramatic cancellation, with the actual rank falling far below the theoretical maximum. Let's pull back to the big picture. Every matrix of rank R is the sum of exactly R rank 1 pieces, the atoms of linear algebra. This is worth highlighting as a core result. This decomposition drives powerful tools across applied mathematics. Let's look at three major applications. First, the singular value decomposition, or SVD. The SVD writes any matrix as a sum of rank 1 pieces ordered by importance. Specifically, A equals sigma 1 times U1 V1 transpose plus sigma 2 times U2 V2 transpose, and so on, where the sigma values are decreasing. The first piece captures the dominant pattern, and each subsequent piece adds the next most significant layer. Second, principal component analysis, or PCA, used throughout data science. PCA peels off rank 1 layers of variance from a data cloud, one at a time. Each layer captures the direction of greatest remaining variation. Third, image compression. Here we keep the most important rank 1 terms and discard the rest, storing a massive image with far less data. The first rank 1 layer gives a blurry approximation, and as more layers are added, the image sharpens. Now, the specific rank 1 pieces are not unique. The vectors can vary, but the count always equals the rank. So next time you see a matrix, don't see a grid of numbers, see the atoms stacked together. A matrix is not a grid of numbers, it is layers of atoms. That is what the matrix truly is.